Okay, welcome. This video is going to talk about what we did at the very beginning of the year, the first few days this week, basic math review of some stuff, and our first little lab activity. We are going to talk about estimation techniques, literal equations, basic trig functions, inverse trig functions, and what we should have in terms of our data and lab work from our inclinometer lab, estimating the height of the balcony in D building, for when we return on Monday. Let's go. Literal equations, we mean equations, just variables, no numbers. We very much want to be able to manipulate algebraically anything and everything. In this case, our example is estimating the number of spheres that can fit into a container. I've chosen to break the container's volume, or total volume, into V1 and V2, one of which is a rectangular prism, the other is a cylinder. They have different heights involved in those, so notice I've used subscripts to differentiate between height 1 of the rectangular prism and h2 for the height of the cylinder at the top. Then in blue I've had the volume of my ball or sphere, which we could use the volume of the sphere, or like we mentioned in class, we could use the diameter of the sphere to find what the volume of a cube with that diameter would be, with the length equal to the diameter would be. And so our total number of balls in this estimation process is written out in the final equation at the bottom. V total divided by V ball, where V total is V1 plus V2 divided by V ball, equals, and then I substitute in those particular equations for V1 and V2. And I like to keep everything organized with our parentheses, and we have proper subscripts to differentiate between heights. Notice I have different subscripts for the radii, since I've decided to use the volume of the sphere in this example in the denominator. And so I have RC, or R sub C, and R sub B to indicate different radii. This is a good example of two things. One, estimating, which we want to make constant use of when we're doing lab work and when we're trying to solve problems, because estimation lets us know if we're on the right track or not. It helps us think about the reasonability of our results in the lab as well. We also want to use literal equations, meaning we can hold back or refrain from putting numbers into an equation. We just use our letter variables to stand for those measurements, and we want to be able to manipulate or move around those variables, which we'll have more practice with this week, but make sure that we can move them around and solve for any given variable that's in there. Next, and what was implemented in our lab on Friday, was using our basic trig functions, sine, cosine, and tangent. We need to know what the relationships are between those right-angled triangle sides. There they are listed for sine, cosine, tangent, and if you do the SOHCAHTOA thing, use that mnemonic if it's beneficial to you. Remember, these are for right-angled triangles, and the sides opposite and adjacent and hypotenuse, these are in relation to specific angles, so it depends where the angle is that we're talking about. In my image down at the bottom left, there the opposite side is opposite of the blue angle theta. Theta, the Greek letter, that is the circle with the horizontal line through it. Other than our basic trig functions, we also have the reciprocal functions. Reciprocal functions are different from inverse functions when it comes to our trig functions. Reciprocal functions are these, and we won't really need to use them unless we're solving a problem and it becomes easier or more elegant to simplify a few different trig functions into some reciprocals. Otherwise, we're mostly, almost always, just going to use our basic trig functions of sine, cosine, and tangent, and our inverse trig functions, the arc functions, sine to the -1 power, cosine to the -1, or tangent -1. Okay, so arc sine, this I always say in class, arc sine, arc cosine, or arc tangent, to make sure I'm being clear. And those arc functions get us back to the angle, or the arc, that is represented by the relationship of those side lengths. So, in our example, our warm-up problem on Friday, we had calculate the height of the building, right? And we were given some information. This is the data we were given. We listed drew a little picture. I've listed what we know and what we don't know. So we know theta, we know HA, the adjacent side's length, and we want to find H HO, or the opposite side's length, which is the height in the example from that warm-up problem. And so after listing what we know and what we want to find out, we have a picture there to help guide us. You can write out your SOHCAHTOA, or if you know your relationships, then you can identify which trig function or which relationship between sides is relevant for finding out what we want to know. So in this case, the tangent function is relevant because we want the opposite side and we know the adjacent side. This was also true for our lab activity in finding the height of the balcony. So we write out our relevant equation. Notice I haven't substituted any numbers in yet until now. So after I've identified what function to use, I've solved for the quantity I want, h sub o, the height of the building. And once I have it solved and isolated that variable I want to find the value of, then we can go in and substitute our numerical amounts. So that was 67.2 meters, tangent 50 degrees, and we have an answer rounded to 3 digits. 80.1 meters is the height. Now in the example on the bottom left, I'm using the arctangent function to go back and find the angle. So the button you're looking for on your calculator, if you haven't used it, is tan -1. That's the button you want to use. Parentheses should open up, and you're putting in this ratio of the opposite side divided by the adjacent side. That's what the tangent relationship is. So the arctangent goes from that ratio of the opposite side divided by the adjacent side, and it takes you back to the value of the angle theta. All right, if I get the tangent of the angle theta, then the result after I push the equals or enter button on my calculator, the result I get is that ratio, HO divided by HA. So arctangent goes in the opposite direction back to the angle, tangent of the angle goes back to the ratio of those side lengths. Okay, so it gets me back to 50 degrees there. I've rounded to 3 digits because that's what our data is presented as, having 3 significant digits. One other method I'm sure I've had plenty of practice with, we need to just review briefly, is the Pythagorean theorem, which we will use to find resultant vector lengths or values. And so here's an example of using my Pythagorean theorem to find the length of the hypotenuse, or the line of sight length, from the balcony to the ground, or from the top of the building to the ground. I want to be able to solve for h sub h, which is equal to the square root of h0 squared, or ho squared plus ha squared. Or in other words, if a squared plus b squared equals c squared, I want to be able to solve for a, b, or c. The final answer here is going to be a positive value because it's a height. And so we have rounded 105 meters. And in the bottom left there you have another example of using an arc function to go back to get the angle. So notice my hypotenuse length is rounded to 105 meters. I use the arc cosine, the relationship between the opposite side and the hypotenuse. I found the opposite side, also a rounded value now, at 80.1 meters, divided by 105, the rounded value for the hypotenuse that I got using my Pythagorean theorem. Arc sine of that relationship is 49.7 degrees when I round it to 3 digits. And then I've written over there in green again, just so we remember that because we do some rounding, we don't always end up with the exact same value every time. Okay? So if I were to plug back in 104.55 for the length of the hypotenuse in my arc sine equation, I would actually end up with 50.00, some odd number of digits after that, degrees for my angle theta. So just be aware that your rounding based on uncertainty of your measurement device is going to affect how you check your work and whether you end up with the exact same number. All right? So within a small percentage difference, we're okay. All right? So our arc sine took us back to that angle. Final word, math-wise this week, it's been 3 days. We want to be comfortable with estimation. Estimation is fantastic. Good habit to practice. Tells us about the physical reasonability of our results in the lab and in problems. Literal equations. We want to be able to manipulate equations that have no numbers in them. We want to be extremely comfortable doing that algebraically. 3, basic and inverse trig functions are pretty much all the trig we're going to need. We'll get to our unit circle when we talk more about simple harmonic motion and oscillations. The reference unit circle is a great thing to just have in your back pocket as a reference. math-wise, that's what we're covering so far. If you want a little more review or need a little more practice, look on YouTube. There's some good videos just to brush up on those trig relationships and manipulating algebraic equations. We'll do a little more with literal equations next week, a little more with Pythagorean theorem and our trig functions when we talk about vectors. Otherwise, when you come in on Monday, we need to have our calculated value for the height of the balcony to the floor in D building. We should have shared our data, so everybody has the data that we collected. We should be able to present a little bit about what your calculated value is and what your range of uncertainty is, so that when we go out to the landing again on Monday and do a direct measurement, you can tell me what your percent error is. Okay? Good job, everybody. See you on Monday.